polynomials, like x to the fifth, right? We know the derivative of that is 5x to the fourth. That's called the power rule. We know how to take the derivative of e to the x. It is e to the x. We know how to take the derivative of the log functions, right? Did y'all learn what was the derivative of ln u?
1 over u.
1 over u, just the derivative of u. Yeah. You learned, we know the derivative of trig functions. Okay, and so what do we have left to learn? There's some more functions that we don't know. We don't know the derivatives of the inverse trig functions. And these are really very interesting derivatives. We're going to be in trigonometry today, so that'll be fun. Triangles and rethinking some stuff about trigonometry to derive the derivatives of the trig functions, the inverse trig functions. And they are different. They do not look like, like the derivative of inverse sine is not inverse cosine. Okay? It's much different. If you have that derivative and integral sheet in front of you, if you don't have it, you should. Print it out, bring it next time. You really need to have that sheet in front of you because I need to help you decipher that sheet, explain to you what it means. And then I would expect that on your test, you may, since the test is online, I would expect that perhaps you have that sheet next to you. It would be to your benefit to have some of the basic derivatives memorized. But the inverse trig functions, I don't know. I don't have them memorized. I mean, some of them are stuck in my head, but some of them are they fly around a little bit. And I might have to look at the sheet to remember them or I derive them. Okay, so let's get busy with some trig. First part's just going to be some basic trig, and then as we move on, we're going to get into derivatives. All right, so the first question is, what do the inverse trig functions give you? All right. The inverse trig function, remember, when you take the sine of 30 degrees, it gives you the ratio that's associated with a 30-degree angle. Remember, the triangle, it doesn't matter what size triangle it is, how big the triangle is. If you have a 30-degree angle in the right triangle, if you have a 30-degree angle, the ratio of the opposite to the hypotenuse will always reduce down to 1/2. That's the whole beauty of trigonometry. It's just dealing with ratios. So you can have a big giant triangle, right triangle, or a little bitty right triangle. If the angle is 30 degrees, then the ratio of the opposite to that angle, 30 degrees, divided by the hypotenuse, those lengths will reduce down to 1/2. The sine of 30 is 1/2. Okay? So the inverse trig functions give you the angle associated with a particular ratio. So the inverse sine of 1/2 is 30 degrees. You may say to me, but Ms. Brooks, there's lots of angles on the unit circle that have a sine ratio of 1/2. And you probably remember that because of that, we had to restrict the domain of the inverse sine in order to only choose the angle between negative pi over 2 and pi over 2. We'll only report that 30-degree angle. We're not going to report the 150-degree angle that also has a sine ratio of 1/2. In order for the inverse trig function to be a function, you can only, for a given ratio, for a given 1/2, you can only get one answer, right? And so then we restrict it. So the first question, what do the inverse trig functions give you? They give you the angle associated with a particular trig ratio, the angle. So tonight at dinner, when your parents say, what did you do? Or your wife or your friends, what did you do today? You said we talked again about inverse trig functions. Inverse trig functions give me the angle, Mom, associated with a particular ratio. A particular trig ratio. Do you talk about math with your parents? Becky and I have math conversations all. Right now, she's still young enough, and I need to be more like, no, yes, you're right, baby. But I'm kind of like, yeah, no, duh. But she's still stuck on 5 minus negative 6. It's messing with her mind. You know, I'm like, baby, double strike and get over it. You know, she just wants it. She wants it to be 11, or I don't know, 1, or I don't. She just, it's not there. You know, she doesn't want it to be 11. She wants it to be 1. or -1, or I don't know. She's all messed up. Okay. So we have these conversations. We'll be just talking. And then she'll be like, no, it's not. I'm like, okay. Recall the graphs of the inverse trig functions from page 223 of your text. Note their domains and ranges. Okay, so notice my inverse trig function here has a domain between -1 and 1. Remember, do you remember the sine function? I saw the sine and opened up my eyes. I saw. Remember him? He looks like this, right? Sort of. Maybe yours is more attractive. But you know, like this is 0 and this is 2 pi and this is pi, right? Those are the places where it's 0. And then this is between, it has a range from -1 to 1. Well, inverse functions flip the domain and range. So the range of the sine becomes the domain of the inverse sine. So that's why the inverse sine has a domain between -1 and 1. You can't take the inverse sine of 5. No function will have a trig ratio of 5, right? The trig ratios for sine and cosine are always between -1 and 1. The side opposite of the hypotenuse. Because if it were greater than 1, that would mean that the side opposite is greater than the hypotenuse, which doesn't make any sense anyway. Okay? Now, we have to choose the range because the domain of the sine function is -infinity, +infinity, but that's not going to work for the inverse sine. So we just select the part of the sine function from -pi/2 to pi/2. That's the part that we use for the inverse sine function. So for the inverse cosine, it also has a domain that is equal to the range of the sine. So from the cosine, from -1 to 1. But we select the range of the inverse cosine to be between 0 and pi. It's a little bit arbitrary what we choose to be the range. Do you remember the tangent function? It has asymptotes. You remember that? It looks like this, and it has a bunch of asymptotes. It kind of repeats, and then it looks something like this in between, right? So the domain of the tangent function, it was undefined at multiples of pi/2, like at pi/2 and 3 pi/2, and odd multiples of pi/2. Those were where its vertical asymptotes were, because that was where a tangent is sine over cosine. That was where the cosine was 0. You know, follow me? And so what we do is we just take one piece of it and flip it. So we sandwich it between -pi/2 and pi/2, but you notice that the domain for the inverse tangent, you can take the domain is from -infinity to +infinity, but our range is from -pi/2 to pi/2 because it's switched. Okay, for inverse secant, it's kind of weird. You remember the inverse secant was the u's, and we only take one piece of it. We look at it between, for x is less than -1 or x is greater than 1, and our range is for values between 0 and pi, but of course you have a horizontal asymptote at pi/2. That's impossible to occur. All right, and then here's your inverse cosecant and your inverse cotangent with their interesting domains and ranges. Okay, so if I want to answer, these are not calculus questions, these are trig questions. If I want to solve the inverse tangent of 1, that means for what angle is the tangent ratio 1? Okay, so when you get 1 for what angle do you get a tangent ratio of 1? Think about your unit circle. When will the tangent ratio be 1? Anyone? The tangent is sine over cosine. In order for the ratio to be 1, they would have to be equal. The sine and cosine have to be equal. Who remembers when the sine and cosine are equal? Robinson? There it is. Okay, so this is true when theta equals pi/4. So if this is equal to some angle theta, that's true when theta equals pi/4. But you may say to me, well, Ms. Brooks, why not in the third quadrant what is that, 5 pi/4? when it's negative, they're both negative, so it reduces to 1. Well, the values that you're allowed to spit out for the tangent are between negative pi over 2 and pi over 2. That's your range. So 5 pi over 4 isn't between negative pi over 2 and pi over 2. You're only allowed to give me the number between negative pi over 2 and pi over 2 where that's true. If you type this in your calculator because you know you're weak and you can't think for yourself, then you could change your mode to degree. I'm just kidding. I don't care how you get the answer, unless you ask your neighbor. And then you do inverse tangent 1. It will tell you 45 degrees, and then you'll remember to multiply that by pi over 180 to make it radians, and then you'll get pi over 4. So I'm okay if you do it that way. All right. Inverse secant is equal to negative square root of 2. All right, this is a little bit trickier. I like to say that I want to find the angle theta so that the secant ratio is negative square root of 2. Well, that is the same as saying that the secant of some angle theta is equal to negative square root of 2. So I just put it in different language, right? And this is the same as saying 1 over the cosine of theta is equal to negative square root of 2. And that is the same as saying the cosine of theta is equal to negative 1 over the square root of 2. Right? Go with me? Just flipping. And this is, of course, equal to negative square root of 2 over 2, which may be familiar to you. So in order to figure out what theta is, you can take the inverse cosine, and you do the inverse cosine of negative square root of 2 over 2. And so this is asking for what value, for what angle will we get a cosine ratio of negative square root of 2 over 2. And if you look on your unit circle, you should see that that occurs at 3 pi over 4. No, just... yes, at 3 pi over 4. So this is true when theta equals 3 pi over 4. You could also do the inverse cosine of negative square root of 2 over 2 on your calculator, or even just 1 over the cosine, negative 1 divided by the square root of 2. And I'm in degree mode, so it's going to give me a degree measure, or not. Oh, sorry, I didn't do inverse cosine. Inverse cosine, negative 1 divided by the square root of 2. And it gives me 135, and I convert that to radians by multiplying by pi over 180. So if you're forgetting some of this stuff, you can always use your calculator as a tool. But I hope that you also look at your circle and kind of feel how that is 3 pi over 4. Okay, Robinson, when is the inverse sine equal to 1/2? For what angle is that true?
That says
Pi over 6.
Very nice. When theta equals pi over 6, you get a sine ratio of 1/2. All right, when is the inverse tangent equal to negative 1? All right, so that's still saying when is the cotangent of theta equal to negative 1, which is really the same as saying 1 over the tangent of theta is equal to negative 1, which you can reciprocate that, but since it's 1, it's just really asking when is the tangent of theta equal to negative 1. And this is really tricky. This is saying what is the inverse tangent of negative 1, which if you do that on your calculator, it will give you negative 45 degrees, right? But the cotangent is defined from, where's my cotangent? The cotangent is defined between 0 and pi, between 0 and 180, right? So negative 45 is here, right? What is its friend from 0 to 180? Well, that would be 135. And that is 3 pi over 4 is the answer that you would get. So here, theta is equal to 3 pi over 4 because the cotangent, the inverse cotangent, is defined between 0 and pi. It only gives you answers between 0 and pi, and negative pi over 4 is not between 0 and pi. So you have to find the one that is. So that's kind of fun. All right. So this is good. If you know that there is some angle alpha such that the inverse sine is 5/13, I'm going to ask you to find the cosine, the tangent, the secant, the cosecant, and the cotangent. Okay. If I know that alpha, the angle, is equal to the inverse sine of this ratio, then I know that the sine of the angle must give me this ratio. All right? And the sine is opposite over hypotenuse. So I can draw a triangle, and I can put alpha on it, and the opposite of alpha is 5, and the hypotenuse is 13. And this is a right triangle. And I can use the Pythagorean theorem to figure out what this side is. This side is the adjacent side to alpha. You remember that a squared plus b squared equals c squared. So 5 squared plus b squared equals 13 squared. So b equals 12. 169 minus 25 is 144. And take the square root and you get 12. You may remember that's a Pythagorean triple. Okay, so then the cosine of alpha, cosine is opposite over hypotenuse. And so the cosine of alpha is 12, cosine is adjacent over hypotenuse. And so it's 12 over 13. The tangent is opposite over adjacent, which is opposite is 5 over adjacent is 12. And then do you guys remember how to get secant, cosecant, and cotangent? Secant is the reciprocal of the cosine. So that's going to be hypotenuse over adjacent, which is 13 over 12. Cosecant is the reciprocal of the sine, which is going to be hypotenuse over opposite, or 13 over 5. And cotangent is the reciprocal of the tangent, so that's 12 over 5. Okay? Just bringing some stuff back. Is it coming back to you? Sort of? Okay, well, here's a fun problem. Find the tangent of the inverse sine of negative 1/2. All right, well, you can only take the tangent of some angle theta. We want to find the angle theta such that its ratio, its sine ratio, is negative 1/2. So the sine of theta is equal to negative 1/2. That's what they're telling us, right? Okay, so you could do this with your calculator, or you can do it with your brain. So, can you guys tell me what the inverse sine of negative 1/2 is? When is that? What is that? On your calculator or with your brain, what do you get? Yeah, not quite 30. Yeah, it should give you negative.
Our screen's frozen. We can't hear you or see you right now, so.
Oh,
yeah.
Okay. But you can hear and see yourselves, or what? I don't know. Oh, they're resetting maybe. Okay. So, can you tell me the inverse sine of negative 1/2? Did y'all get it?
Negative pi over 6.
Negative pi over 6. And so, because it was negative 30 on your calculator, you convert to radians, is negative pi over 6. And the tangent then of negative pi over 6, tangent is sine over cosine. The sine of negative pi over 6 is negative 1/2. The cosine is the square root of 3 over 2. So this becomes negative 1 over the square root of 3 is your answer, which you can rationalize to be negative square root of 3 over 3 by multiplying top and bottom by square root of 3 over 3. Okay? All right. This problem is kind of fun. The secant of the inverse tangent of 1 plus the inverse tangent, or the inverse cosecant of 1. All right, we already did the inverse tangent of 1. We found that to be pi over 4. Now, the inverse cosecant is the same as considering the inverse sine of the reciprocal of 1, which is still 1. So when is the sine 1? When is the sine 1? Yeah, at pi over 2. So this is asking for the secant of pi over 4 plus pi over 2, which is asking for the secant of a half plus a fourth, which is 3/4. 3 pi over 4. The secant is 1 over the cosine. So this is asking for 1 over the cosine of 3 pi over 4. The cosine of 3 pi over 4 is 1 over the square root of 2, negative. So this is 1 over square root of 2, negative, and so your answer is negative square root of 2. Okay. All right, let's look at another problem. Have y'all noticed that this is all just trig, right? We haven't done any calculus yet. So we're just kind of reviewing some trig. All right, remember that the inverse function returns an angle theta. So the secant of theta is what we're looking for, where the tangent of theta equals x over 2, because we're told that the inverse tangent of x over 2 is equal to some angle, so we can rewrite that. Now the tangent is, taking oats away, opposite over adjacent, right? However you have that memorized. So that means if we were to draw a right triangle and pop a theta right here, the opposite is x, the adjacent is 2. And so the hypotenuse is the square root of this squared plus this squared, or 4 plus x squared, right? So now the secant of theta is the same as looking for 1 over the cosine of theta, or if you think the cosine is adjacent over hypotenuse, so this is going to be hypotenuse over adjacent. The hypotenuse is square root of 4 plus x squared over the adjacent, which is 2. Make sense? All right. So, similar, you can do this problem. The inverse sine is equal to, the inverse sine of x is equal to some angle theta. So we want to know what the cosine of theta is. That's what we're really asking. So right here, this tells us that the sine of theta is equal to x. I'm going to put that over 1. What's the ratio for sine? Opposite over hypotenuse. Is that familiar? Yeah? Okay, so this is opposite over hypotenuse. So that means if I draw a right angle and put a theta here, the opposite is x, the hypotenuse is 1. The Pythagorean theorem tells me that this is going to be the square root of the hypotenuse squared minus this side squared. So this is going to be 1 minus x squared, just using the Pythagorean theorem. Okay? Now, I want the cosine of theta. Cosine is adjacent over hypotenuse, which is equal to the adjacent, which is square root of 1 minus x squared, over the hypotenuse, which is 1. So just the square root of 1 minus x squared is the answer.
So when y'all taught us, or you taught us last,
You can do
no,
some old horse caught another horse taking oats away, or you can do some old hippie caught another hippie tripping on acid.
I remember
Okay.
that one.
Yeah, that's pretty plain. Okay, it says evaluate the following limits. We want to know the limit as x approaches 1 from the left of the inverse sine of x. So probably the easiest way to do this is to look at your graph and look at your graph. Here's your graph of the inverse sine. We wanted to approach, what do we want to approach? 1 from the left. So as you come into 1 from the left, what's your y value going to be on the inverse sine function? Yes, from the graph, it is pi over 2. Also, from the graph, let's look at this one. The limit as x approaches infinity of the inverse secant of x. All right, so let's look at the inverse secant. As x goes to infinity, what does it look like it's approaching? Yeah, it's got a horizontal asymptote at pi over 2. So as x goes to infinity, the inverse secant approaches pi over 2. Also from the graph. Okay, how about the inverse tangent as x goes to negative infinity? This is a real important one. It comes up a lot. The inverse tangent graph is worth sticking in your brain. Just remember, it's the little s sandwiched between negative pi over 2 and pi over 2. As x goes to negative infinity, you're going to be looking towards that horizontal asymptote at negative pi over 2. Did y'all see that? As x goes to negative infinity, the y value is going to get closer and closer to negative pi over 2. That one shows up a lot in other coursework. So all of those we just found from the graph. Okay, now the whole reason we're doing this is because we wanted to figure out what the derivative of the inverse sine function is. Okay? So we're going to use some of the strategies that I just reviewed with you and some of the skills that we've already learned to derive the inverse sine. And we're not going to derive them all. You're going to see how to derive this one, and then on your own for fun you can, derive the rest of them if you want. Okay. Now we know what this means. Y equals inverse sine x. This means give me the angle, here it'll be y, where the sine ratio is x. Okay? So this means that the sine of y has to equal x. And just to be consistent with what I've been doing, I'm going to say x over 1. Okay? Because this is the angle that has x as its sine ratio. So I can just take like the sine of both sides, right? Okay, and the sine is opposite over hypotenuse. So that means that I have a right triangle with an angle y, and the opposite is x, the hypotenuse is 1. If for fun I wanted to find the adjacent, what would it be?
Square root of 1 minus x.
Square root of 1 minus x squared, just using the Pythagorean theorem. This squared minus that squared, take the square root. Okay? All right, now, this right here, the sine of y equals x, I can differentiate that with the skill that the last lecture or 2 lectures ago, implicit differentiation. Remember implicit differentiation? Y is not defined explicitly in terms of x, but I could do it implicitly. So I will differentiate this implicitly. Okay, so that means I'm going to take the derivative with respect to x of the sine of y, and I'm going to take the derivative with respect to x of just x. All right, well, what is the derivative with respect to x of the sine of y? What's the outer function is the sine. What's the derivative of the sine? Okay, so it's going to be cosine of y times the inner function, the derivative of the inner function, which is dy dx. Right? That's your implicit differentiation. What's the derivative with respect to x of x? 1. Y'all with me? Now, what do we do in implicit differentiation? What was the thing that we did?
For the dy dx back.
Yeah, we solve for dy dx. Good. And so this is going to be dy dx equals 1 divided by the cosine of y. Right? So I found the derivative, but I don't want my answer in terms of y. I want my answer in terms of x. Right? Okay? So this is the derivative, but I want my derivative in terms of x. Well, up here I have a triangle, and if I wanted to find the cosine of y, could I not tell you what it was in terms of my triangle? The cosine is what? Adjacent over hypotenuse. The adjacent is the square root of 1 minus x squared. The hypotenuse is 1. So the cosine of y in terms of x is the square root of 1 minus x squared over 1. Okay? So from the triangle above, the cosine of y is equal to the adjacent over the hypotenuse, which is just going to be the square root of 1 minus x squared over 1, which is just the square root of 1 minus x squared. So my derivative which is dy dx, instead of 1 over cosine y, 1 over cosine y, I can say what cosine y is. I just determined that the cosine of y was the square root of 1 minus x squared, so that's what I'll put here. Okay? And that is the derivative of inverse sine x. So the derivative with respect to x of the inverse sine of x is equal to 1 over the square root of 1 minus x squared. Interesting, right? It doesn't have a cosine, an inverse cosine in it. The derivative of the inverse functions are in terms of x. They don't have any trig functions in them. It's kind of cool. I feel sadness because of the trig. I'm feeling y'all going, God, I wish I learned that unit circle. But it's actually pretty fun because we put two things together. We did some trig, which you did learn at one point in your life, and then we combined that with implicit differentiation to derive the derivative of the inverse sine function. This is what I need. Here is my derivative. That's what I was looking for. And the rest of the inverse trig functions can be found in the same manner. But I'm not going to find them. I'm just going to give them to you. Okay? All right. So I want to take a minute to bring to your attention the way that the little sheet gives you the derivatives so that you can understand what they're talking about. What they do is they're telling you the derivative with respect to x of some function, like the inverse sine, of another function, say u, okay? The sheet is trying to tell you that you would use the chain rule. You would take the derivative of the outer function, which is 1 over the square root of 1 minus u squared, and then, because that's the derivative of the inverse sine, and then you would take the derivative of the inner function, which is du dx. So the sheet, that's why it has u prime over the square root of 1 minus u squared on it, because it's kind of reminding you that you may have to have the chain rule in there. So if I ask you to find the inverse sine of 2x, you would do 1 over the square root of 1 minus 2x quantity squared, but then you'd have to take the derivative of 2x, which is 2. And that's what you would put up top. Does that make sense? So that's what once we do some more of these, it should make sense to you. Now we do have a restriction because we're taking the inverse sine of u, remember the sign is defined, you can only take the inverse sign of values between -1 and 1. And you can, from a notation perspective, if you want to sandwich something between -1 and 1, that's the same as saying the absolute value is less than 1. Those are numbers, absolute value sandwiches it in between -1 and 1. All right, the derivative with respect to x for the inverse cosine of some other function u, this is without proof, is very similar to the inverse sign, but it's negative u prime over the square root of 1 minus u squared, where, again, the absolute value of u has to be less than 1. So you have to, I'm incorporating the chain rule into my derivative. That's where the u comes from. So a lot of times in engineering, you get these huge books with all these derivatives and integrals already done for you. But part of the technique is you have to be able to figure out what that formula that they give you, what stands for what. Okay? And so that's what I'm trying to do here for you. The derivative with respect to x of the inverse tangent of some function u is u prime over 1 plus u squared. It's worth memorizing, that one. All three of these are worth memorizing. And for some reason, the inverse secant shows up a lot in nature, so that one may be worth memorizing too. The derivative with respect to x of the inverse secant of u is equal to, this is a weird one, u prime over the absolute value of u onto the square root of u squared minus 1. And the restriction on that one is that the absolute value of u has to be greater than 1. All right, and then you have your inverse cotangent. It's very similar to the inverse tangent. What do you think, if you know that, based on what the cosine is? Do you have a guess for the inverse cotangent? It's exactly the opposite. It's just negative u prime over 1 plus u squared. And the derivative with respect to x of the inverse cosecant of u is equal to negative, same as this, but with a negative. Negative u prime over the absolute value of u times the square root of u squared minus 1. With the absolute value of u greater than 1 is your restriction. Okay? So now we have all of our derivatives of the inverse cosine, sine, tangent, secant, and cosecant functions. You also know e to the x and ln x and all the sine, cosine, tangent functions, so you can just go to town with the derivatives, which is what we are going to do now. What will be the derivative of the inverse cosine of x squared? Okay, we're going to use the chain rule. We're going to recognize, what is my u here? In this problem, my u is, do y'all agree it's x squared? So my u prime is 2x, right? The formula for the derivative with respect to x of the inverse cosine of u is negative u prime over the square root of 1 minus u squared. That's what the formula tells you, okay? So you have identified specifically for this problem what u prime is, right? For this problem, u prime is 2x. So it's going to be negative 2x over the square root of 1 minus u squared, which is x squared. So this will be x to the 4th, because it's x squared squared. Okay? So once you know how to read the formula, it's pretty easy. So for the inverse secant function, your u here is 2s plus 1. So u prime is just 2. All right? According to the formula, the derivative with respect to x of the inverse secant of u is equal to u prime over the absolute value of u times the square root of u squared minus 1. Okay? So here it will be u prime, which is 2 over the absolute value of u, the absolute value of 2s plus 1, onto the square root of 2s plus 1 squared minus 1. And if you want, you can clean this up a little bit. This is 2 over the absolute value of 2s plus 1 square root. Okay, 2 squared plus 1 quantity squared is 4s squared plus 4s plus 1 minus 1. The minus 1 from right there. You all okay? So I just FOILed this out. Notice the 1's cancel, and you have a 4s squared and a 4s. So you can actually factor 4 out of that. So this is absolute value of 2s plus 1 on the square root of 4 times s squared plus s. But the square root of 4 is 2. So you can think of this as 2 over the absolute value of 2s plus 1 times 2 on the square root of s squared plus s. And your 2's cancel, and you get 1 over the absolute value of 2s plus 1 onto the square root of s squared plus s. Done? Yes. All right, let's really chain it up here. All right? We're doing the inverse tangent of x, but we're taking the natural log of it. So this now is my u, the inverse tangent of x. All right, you learned hopefully from the last lesson that the derivative with respect to x of the ln of u, this is on your sheet, the derivative with respect to x of the ln u is what? Times u prime, right? If you look at your sheet, you'll see it. It'll say u prime over u, right? Well, our u here is the inverse tangent of x, right? That's what our u is for this problem. So we're going to also need to know the inverse tangent of whatever, a function. Now, this is a different u, but the inverse tangent of u is u prime over 1 plus u squared. So you have to get your brain kind of around all of this stuff. So if our u from here is the inverse tangent of x, then u prime that we're going to be using, the u that we're using for here, this is my u, and u prime, the inverse tangent, the derivative of the inverse tangent of x, well, the derivative of x is just 1. So the derivative of the inverse tangent is just, it's just going to be 1 over 1 plus x squared. Does that make sense to y'all? Because the inverse tangent, the derivative of x is 1. So when you do this one, it's just going to be 1 over 1 plus x squared. Okay, so we're going to plug this u prime is going to go in there. The u is going to go in there. And you're going to be done. So you're going to have y prime is going to be u prime, which is 1 over 1 plus x squared, over u, which was inverse tan of x. So this is 1 over, you could write this as 1 plus x squared times the inverse tan of x. All right, inverse cosecant of u, where u is e to the t. Okay. If u is equal to e to the t, what is u prime?
E.
Very good, e to the t. All right, the inverse cosecant, the derivative with respect to, in this case, t, of the inverse cosecant of some function u is, if you look at the formula, negative u prime over the absolute value of u on the square root of u squared minus 1. Okay? So our u prime here is e to the t, so this is negative e to the t over the absolute value of e to the t times the square root of e to the t squared, which is e to the 2t minus 1. Now, the absolute value of e to the t, you don't actually need those absolute value bars because e to the t is always positive. It's an increasing function that can never be negative because the base is positive. So you can actually think of this as e to the t over e to the t, which cancels. So this is negative 1 over the square root of e to the 2t minus 1. All righty. What fun are we going to have on number 14? It's not fun, Miss Brooks. We're in hell, okay? I can feel it. You're here. Is it hot? Are you hot now? You're okay? All right.
When I'm doing work is when I start sweating.
Okay, watching me do it. It's not nearly as bad as actually trying to do it yourself. All right. Okay. Where are we now? What rule do we get to apply on this problem, number 14 here? Do you guys see a product rule? Yes or no? I got a U here and a V here, right? Y'all see that? That's what I was looking for. Okay, so the product rule is U times V prime plus V times U prime. Oops. Okay, so our U, where our U is equal to X, so our U prime is equal to 1, and our V is equal to the inverse sine of X, so our V prime is the derivative of X, which is 1, over the square root of 1 minus U squared, because our U here is just X. So it's U prime over the square root of 1 minus U squared is the derivative of the inverse sine. Okay, so Y prime is U, which is X, times V prime, which is 1 over the square root of 1 minus X squared, plus V, which is the inverse sine of X, times U prime, which is 1, plus, what is the derivative of this? Well, you can think of this as 1 minus X squared to the 1/2 power. So the 1/2 comes in front. You rewrite this, 1 minus X squared to the 1/2 minus 1, which is negative 1/2, times the derivative of that, which is negative 2X. Derivative of the inside, using the chain rule. Okay, so this is X over the square root of 1 minus X squared, plus the inverse sine of X. The 2's cancel here, so this is going to be minus X over the square root of 1 minus X squared. Well, that's kind of fun, right? So these cancel, and your final answer is just inverse sine of X. Isn't that cute? So the derivative of that, who would have thought? Not B. All right, do we have a couple more? Find the right and left end behavior model of the inverse tangent of X and describe any horizontal tangents. They really just want you to recognize end behavior is horizontal asymptotes. And so I just want to bring to your attention, I want to talk about the inverse tangent again. I guess it does show up a lot in life, or in mathematical and engineering life. So if you could memorize that the inverse tangent is the little s sandwiched in between negative pi over 2 and pi over 2. That would be a good thing for you. Just something to have in your toolbox along with all the other stuff. Okay? And so the end behavior is just what it looks like. What does the graph look like as x goes to positive infinity or as x goes to negative infinity? Well, it looks very much like the line y equals pi over 2 and y equals negative pi over 2, right? So that's the horizontal asymptotes. So the horizontal asymptotes y equals pi over 2 and y equals negative pi over 2 are the end behavior. Okay, and that's really asking what is the limit as x approaches infinity of the inverse tangent of x. Well, that's pi over 2. And in the same light, the limit as x goes to negative infinity of the inverse tangent of x is what? As you go to negative infinity, where are you approaching? There you go. Thank you. Negative pi over 2. So that's just, I don't know, they put it in this section again just to remind you. The inverse tangent function is one that appears a lot, so it's a good one to remember. So that's it for this section. It's a lot of practice with derivatives.